Students, today in this session we are going to start our fifth module. So this module is dealing with a Rayleigh flow. A Rayleigh flow. So what is actually a Rayleigh flow? Rayleigh flow is a compressible fluid flow where our main driving potential is heat addition, heat transfer. It can be either heat addition or heat rejection. So driving potential here is heat transfer. Okay. So we have studied different types of flow like isentropic flow. So in isentropic flow, fan flow. So two types of flow, fan flow, and okay, again isothermal flow. Isothermal flow also we have studied. In isentropic flow, mainly the driving potential is variation area. In fan flow, it is actually friction. Okay, friction along the wall of the surface of the duct. Isothermal means here the temperature should remain constant. So that is the idea behind isothermal flow. So in isothermal flow there will be certain amount of friction and the duct area will be constant. So these are the different types of flow that we have studied in the previous modules. So today we are going to learn Rayleigh flow whose driving potential is heat transfer. So it is actually a simple flow considering the effect of heat addition or heat rejection. So it's a simple flow, a compressible fluid flow. So in order to assumptions that we take so that we can consider a particular flow as a Rayleigh flow based on these following assumptions. So assumption for being or the characteristics. Okay, the characteristics or assumptions. The flow should be the flow should take place in should take place in should take place in constant area duct. Constant. So area of the duct should not vary. The cross-sectional area of the duct should not vary. That is a very important point. If that varies means it will be a bit complex flow. So it won't be a simple flow. Okay. Simple flow means there should be only one driving potential. Okay. If there are more than one driving potential means it is no more a simple flow. Okay, so if it is not a simple flow means it will be very difficult to analyze the flow. Okay, so this is the first assumption. Second one is the frictional effects. The friction is negligible. Friction negligible. So we can negligible. Okay, so it is not required to take the effects of friction in this case because frictional effects are negligible compared to the heat transfer effects. The third one is there should be no mass addition or rejection. No mass transfer. No mass transfer. Okay. Fourth one should be the gas should be perfect. So the PV equal to MRT, that equation should be valid for the gas we are considering. So the gas flowing should be perfect. Then only the analysis becomes simpler. And fifth one is composition of the gas shouldn't change. Composition of the gas. The composition of the gas doesn't change along during the flow. Doesn't change during the flow. Next one should be the main. This assumption is valid for all types of flow. The flow should be one dimensional steady. The flow is steady and one dimension. One dimension. And no external work should be there. No external work should be there. And there should not be any body forces should be absent. Body forces absent. No body forces. Okay. There should be only pressure force. There should not be any body forces or surface forces. Okay. So these are the assumptions required. Eighth one. Okay, these are the assumptions this should be the characteristics of a Rayleigh flow. Okay. Only heat transfer is the main driving potential. Okay. Then students, what is known as a Rayleigh line? Rayleigh line. Rayleigh line, the frictional flow of a perfect gas, frictionless flow of a perfect gas through a constant area duct in which heat transfer to or from the gas. Okay, to or from the gas. That means heat can be either added or rejected from the gas is dominant factor for what? Bringing about changes in the flow is referred to as Rayleigh flow. That you have understood, right? Or diabatic flow. Diabatic flow means opposite of adiabatic flow. Means there will be a heat transfer. So the main reason for bringing changes in the flow or flow parameters is nothing but heat transfer to or from the gas. Okay, so the flow is a perfect the gas is a perfect gas and the flow is frictionless and it is flowing through a constant area duct, but the only reason for changing the what flow parameters is heat transfer from or to the gas. So this flow is also known as diabatic flow. Then what is the Rayleigh line? Rayleigh line is nothing but a Rayleigh flow which is which is represented by a curve. Rayleigh line is it is a description. It is actually the locus of thermodynamic states. Thermodynamic states traced during a Rayleigh flow. During Rayleigh flow. So Rayleigh line is nothing but locus of thermodynamic states traced during a Rayleigh flow. That is nothing but when a Rayleigh process is represented in a PV diagram or HS diagram or TS diagram, then that particular figure is known as a Rayleigh line. That particular curve is nothing but locus of various states that is through which the system passes or the flow passes. Okay, so that is a Rayleigh line. So students, what are the governing equations? Governing equations. We know there are three types of governing, 3 to 4 governing equations will be there: conservation of mass, conservation of momentum, conservation of energy, and entropy equation. So students, since the flow is taking place through a one-dimensional, the flow is considered as one-dimensional flow in a constant area duct. Actually, rho AV should be constant, right? Rho AV should be constant. But since constant area duct A is also constant, so rho V equal to this can be written as m dot mass flow rate, right? So rho V is nothing but m dot by A is equal to a constant G. Take it as G, okay? And it will be a constant. So this is a mass flux. G is mass flux. So this idea we have already taken. We have already used this kind of idea like mass flux in fan of flow, right? mass flux. So this is the equation for conservation of mass. And simple form of momentum equation is like we know the momentum equation is PA, pressure force plus dynamic force, right? Rho A V square will be equal to the total force acting on the system, and it will be a constant, right? Since A is constant, we can write it as P plus P is nothing but pressure, rho density, V velocity, okay? Rho V square equal to F by A equal to a constant again, right? So P plus rho V square is equal to F by A, or P plus rho V square is equal to a constant. That is another, that's the equation for momentum, okay? Since we can write rho V as G, so V can be written as G by rho, right? So V square is G square by rho square, right? So you please substitute V square here. So the equation will become P plus rho into G square by rho square is equal to a constant, right? So here rho and rho cancel. What remains is P plus G square by rho is equal to a constant. So this is the momentum equation in case of a a Rayleigh flow. Okay, P plus G square by rho is equal to a constant. So students, you can see that here two variables are there, P and rho, or P and 1 by rho. So it's a function of this equation is a function of P and 1 by rho. So P into 1 by rho into G equal to constant. So two variables, P and 1 by rho. So this equation can be represented in a graph with the x-axis P, x-axis P in y-axis and 1 by rho in x-axis. Okay. So this can be represented in a thermodynamic coordinate system with like this PV chart. So here PV means V means actually 1 by rho is nothing but 1 by rho is specific volume, small v, right? So if I take P here, 1 by rho equal to V in y-axis, you can plot this graph like this will be a straight line like this, right? Because P plus 1 by rho into some constant is equal to another constant, right? So it will be this graph will be like this, right? So this is how you represent a Rayleigh line in PV coordinate system. So this is actually a PV system, PV coordinate system. So how can you represent this same process or Rayleigh line in a Mollier diagram? Mollier diagram. So what is Mollier diagram? Mollier diagram is HS diagram, enthalpy entropy diagram. So enthalpy in the y-axis and entropy in the x-axis. So this graph look like this. Okay. If you draw the graph, it will be like this. So students, what should be noted is that there is a particular value for which enthalpy is maximum. So this value is maximum enthalpy. And there is a point where entropy is maximum. S max. Okay. So students, actually this is our equation, P plus 1 by rho into G, sorry, actually G square, okay, forward to that. It is G square equal to constant, right? So when this equation is plotted in a enthalpy entropy coordinate system, it looks like this, okay. So the general shape of the Rayleigh line on an HS diagram remains same for all perfect gas. So for any perfect gas, the shape will be like this only. The shape is such that it passes through one, okay, it passes through one state of maximum enthalpy and one state of maximum entropy. So in the figure you can see that maximum entropy is denoted by this point is denoted by capital S, And the state of maximum enthalpy is denoted by capital H, 2 points, capital H and capital S, right? So the Rayleigh line, uh, along with the corresponding stagnation. So if you, so here only static values are there. So I will show the stagnation values also. Okay, corresponding stagnation value. So HS. Okay, so this will be the shape. This will be the shape of what? A Rayleigh line. Okay, so now you have to show the corresponding stagnation values. So you know what is stagnation value, right? So I am drawing a line along the capital S point, capital S, this is capital H. Okay, so the stagnation, if the upper part will be subsonic. Okay, I will explain why it is subsonic. Lower part will be supersonic, because static enthalpy value will be lower for what, supersonic, and static enthalpy value for subsonic flow will be higher, right? So naturally the m greater than 1 value will come at the lower portion, and sorry m less than 1 will come in upper portion. So you have to note that. So this is the corresponding stagnation value, locus of stagnation, that be locus of stagnation enthalpy. Okay, and you have to note that this here, the lower branch will be the subsonic value, and upper branch will be the supersonic value. Okay, the exact opposite of the actual line. This will be the, I will draw with another. The line drawn in the blue line is the locus of stagnation enthalpy. Okay, locus of stagnation enthalpy. So you can see that there is a point which touches the this point will be the maximum stagnation enthalpy value, right? So corresponding to this line, the maximum stagnation enthalpy value is this. You can note that the shape of the stagnation enthalpy curve shows that the point of maximum stagnation enthalpy always coincide with what? Always coincide with the S. So here this is maximum stagnation enthalpy, not static enthalpy, stagnation enthalpy. Maximum static enthalpy is capital H. Okay, maximum stagnation enthalpy is this one. So this point always coincide with the maximum entropy, maximum static entropy. Okay, maximum entropy value. So there is no difference between static enthalpy and stagnation enthalpy. Both will be same. So these 2 points always coincide with the same, this small x max. Okay, so later in this module you can see that it has the Mach number at the point of maximum entropy will be unity. Mach number will be equal to 1 in this particular that you will be studying in the coming sessions. Okay, so the upper branch of Rayleigh line above the point of maximum entropy corresponds to subsonic flow, because here static enthalpy, this enthalpy is higher than this particular enthalpy, because in subsonic flow enthalpy will be, static enthalpy will be higher, velocity will be lower, right? Velocity will be lower, so static enthalpy will be higher. But in case of uh, The students have a look at this particular figure. So this is an HS diagram for Rayleigh line. You can see that there is a point H here, so maximum static enthalpy, point S here, maximum entropy, maximum stagnation point. Maximum stagnation point always corresponding to this maximum entropy line. Okay, so this is the locus of stagnation enthalpy. The locus of stagnation enthalpy. This is actually static enthalpy. You can see that I am taking a point 1 here in the subsonic branch. Upper branch will be subsonic because you can see that H1 is higher than static enthalpy is higher for this particular line than the corresponding lower branch line. And you know that in case of subsonic flow, the enthalpy value, static enthalpy will be higher corresponding to the supersonic flow, right? And corresponding stagnation value can be seen here. So this lower branch will be subsonic here, upper branch will be supersonic here. But in case of this particular static line or Rayleigh line, upper branch will be subsonic, lower branch will be supersonic. But here lower branch is subsonic, upper branch is subsonic. Okay, so hope you have understood the difference. So why this anomaly comes, or this variation comes, because here heat addition is normally we write energy equations H plus V square by 2 is constant, but now it is not valid. Why? Because H plus V square H plus 1 H1 plus V1 square equal to H2 plus V2 square by 2 plus heat transfer is also coming. Okay, heat transfer is also coming. So that is why this variation happened. But in the previous cases and all, there is no heat transfer. That is why H plus V square by 2 constant, that particular equation is valid. But that is no more valid here. So when enthalpy is lower, when the enthalpy value is lower, it doesn't mean that velocity will be higher. Okay, because there is a Q value here, so it plays an important role. Okay, so you can see that here corresponding to 1, corresponding stagnation value, stagnation enthalpy is H01, corresponding to H1 H01, corresponding to H2 H02, corresponding to H, it won't be the maximum stagnation enthalpy here. Okay, and corresponding to this value, maximum stagnation enthalpy will be there. So what is the reason? I will tell you. And now you come to the lower branch, m less than m greater than 1, corresponding to 3. You can see here H03 in the upper branch, corresponding to 4 H04. So this P03 is stagnation pressure value, P04 is stagnation pressure value, corresponding to 3 and 4. Okay, 3 and 4. So hope you have understood the concept. And you can see that the velocity value here, you can see that V1 square by 2, this difference is V1 square by 2. So this V1 square by 2 will be increasing when you go, this will be V2 square by 2, right? V2 square by 2, and the velocity continues to increase when you move towards the right. So here 3, for the point 3, this is supersonic value. So for supersonic branch, the velocity should be higher. So this will be the velocity V3 square by 2. You can see here V3 square by 2. And for point 4, you can see that V4 square by 2. V4 square by 2. So the velocity is seen decreasing. The students, please note that in the case of P3, V3 is the velocity, and when you go towards the right in case of supersonic flow, you can see that velocity is seen decreasing. Okay, when you reach here, velocity is even lower. So in case of supersonic flow, when you proceed towards right, that is when you proceed the flow, velocity seems to decrease to a value m equal to 1. But in case of subsonic flow, velocity is seen to increase to m equal to 1. So the point of what the limiting value of Mach number is unity, Mach equal to unity. Okay. Students, now we will proceed to the concept of simple heating process. Mainly, we have already told you, we have already discussed that the main driving potential is heat addition or heat extraction. So, heat addition means it is a heating process. Heat extraction means it is a cooling process. Now, have a look at this. Let us consider a flow of compressible fluid through a constant area duct to which heat is added at a uniform rate. Okay. So heat is added at a uniform rate. So the heat addition can be due to heat transfer from the surrounding through the wall separate in the flow with the surroundings, or it can be due to combustion reaction that take place in the fluid itself. Okay. In both cases, what happens? The fluid absorbs heat energy and the thermodynamic state of the fluid changes according to the Rayleigh equation, right? According to the Rayleigh flow equation. So I will show you a figure. So this is a figure, HS diagram. You can see this is our Rayleigh line. So this is H, this is S. So this will be M less than 1. Upper branch will be subsonic, lower branch will be supersonic. Okay. I will show you two. This is HS. I will show you two ducts. Okay, here this is section 1, this is section 2, this is section 3, and this is section 4. So some constant flow is happening. M dot is same in both ducts. Here also Q is added, here also Q is added, but difference is here Mach number is less than 1, here is Mach number is greater than 1. That is, here this is subsonic, this is supersonic. So what will be the difference? So corresponding to this same m dot, right? So we can have the same line. Okay. So this will be the upper the duct. For the first duct, it will be the m less than 1, right? So for the first duct, the upper branch will be valid. Okay, upper branch. So you can see that so I am taking section 1 here. Corresponding pressure is P1. And let the second section be here 2. Corresponding static pressure is P2. Okay. Taking the third, the second branch will be in the second duct will be in the lower branch. 3 here, P3, 4 here, P4. Okay, P4. So students, this figure shows two ducts. Okay, let it be A and B. Okay, A and B. Two ducts with the same flow rate m dot. Same flow rate m dot, along with the corresponding line on the HS diagram. You can see here, corresponding HS diagram can be seen here. So we are assuming subsonic flow for the first duct, duct A, and supersonic flow through the duct B. So corresponding sections 1 and 2, 3 and 4, all the 4 sections are marked in the HS line. So students, since you know the second law of thermodynamics, right? According to second law of thermodynamics, addition of heat to a system with a finite temperature change always results in what will be the change in entropy? Entropy will always increase. When heat is added, entropy will always increase. When heat is added, entropy always increase, right? So you have studied in your second law of thermodynamics. Okay, entropy always increase. So when heat is added, what will be the direction? What will be the direction of the flow? So entropy increase means it will be along. It will be towards the right of, for subsonic flow. It will be like this. For supersonic flow, it will be like this. Okay. When heat is added to the flowing gas, the entropy of the gas increases. That means the entropy at the downstream section must be greater than the upstream section. That is important point. Entropy in the downstream. Entropy of S2 should always be greater than entropy of S1, or entropy of S4 should always be greater than entropy of entropy of the S3. So, due to you can see the for supersonic inlet condition that is corresponding to the lower branch, due to heating the state point shift towards right 3 to 4. What will happen to the static enthalpy? Static enthalpy. What is happening to static enthalpy? You can see that in supersonic flow, when heat is added, static enthalpy H3 and static enthalpy H4, right? So static enthalpy increases, right? So from H3 to H4, static enthalpy increases. So when heat is added, static enthalpy increases in case of supersonic flow. So what happens to the velocity? But velocity decreases, right? Because velocity decreases. So you can see here, so you can see that from when 3 to when in supersonic branch, when the flow is moving from left to right, that is 3 to 4, this velocity will be higher than this velocity, right? Means velocity decreases. So when heat is added to supersonic branch, to supersonic flow, what happens? Static enthalpy decreases. Enthalpy decreases. Not decreases, increases, right? Enthalpy increases and velocity decreases. Okay, so the net effect of decreased velocity and increased temperature causes what? Causes what? Mach number. What will happen to Mach number? Mach number also decreases. If velocity decreases, Mach number also decreases. Similarly, for a subsonic inlet, you can see here subsonic inlet corresponding to the upper portion of the Rayleigh line. So this is this particular upper portion. Due to heating, the state point shift from left to right. It shift towards the right? So there is an increase in static enthalpy up to maximum static enthalpy H. And what happens to velocity? What happens to velocity? You can see that. For this particular Mach number, or this particular one, you can see this much is the velocity, and for the second point, the velocity is this much. This will be the velocity. Okay, so the velocity is increasing in case of what? Subsonic flow. So when heat is added to subsonic flow, what happens to static enthalpy? Static enthalpy increases, velocity also increases. So this is the exact opposite of what we have studied in all of the the flow that we have studied in the previous session. So when if h plus v square by 2 is constant, if h increases, and naturally v must decrease, right? But here you can see that h also increases, velocity also increases, and Mach number also increases. So this is not based on this particular equation, but it is based on equation where heat transfer also plays an important role. That is why when h increases, sorry, not like this, h1 plus v1 square by 2 equal to h2 plus v2 square by 2. So this particular equation. So that is why when static enthalpy increases, means velocity also increases. Okay, so that is a difference here. So similarly, you can also represent cooling process. So in heating process, the direction you have already understood, towards right. So what will be the direction of cooling process? Simple cooling process. Simple cooling process will be like the same equation, the same line, with same mass flow rate, but the direction will be like this. Direction will be like this. So for m less than 1, cooling will be towards left. M greater than 1, again cooling will be towards left only. So in a according to law of thermodynamics, extraction of heat from a system with finite temperature change results in decrease in entropy. So if heat is extracted, entropy will definitely decrease. But in an adiabatic flow, always entropy increases only. Entropy change will be positive in an irreversible adiabatic flow. Okay, in a reversible adiabatic flow, entropy always and there won't be any entropy change, or entropy always remains constant. Okay, so those are the difference here. So those are the difference. And you can note that if cooling is taking place from 1 to 2, here 3 to 4, when cooling is taking place in subsonic flow, static enthalpy decreases and velocity also decreases, right? In supersonic flow, static enthalpy decreases but velocity increases. So that's the difference. We'll write it in cooling process, cooling in subsonic, static enthalpy decreases, velocity also decrease. And cooling in supersonic, static enthalpy decreases, but velocity increases. So velocity decrease means Mach number decrease, velocity increase means Mach number increase. So with this I will conclude this particular session. Thank you.